Well, let's look at what happens when we're talking about motion on say, the surface of the Earth. So imagine that we're looking at a map, we're looking down at a map, and I ask you, if I travel 5 miles, then 3 miles, then 2 miles, how far am I from where I started? Now, this is even a worse question than what I asked on the previous slide. Um, at least when I was dealing with 10 and 2, I knew that I would either be 12 steps to the left, 8 steps to the left, 8 steps to the right, or 12 steps to the right. I was narrowed down to those 4 possibilities. Here, I've got possibilities all over the place because I could go 5 miles this way, and then 2 miles this way, then 3 miles this way. I could go 5 miles this way, and then 2 miles back, and then 3 miles back, and end up exactly where I started. I could do all kinds of things. So I have no idea where I'm going to end up if I just specify how far I traveled, and I certainly don't know how far from where I started I'm going to be. So how will we handle this when traversing terrain? When we're look at a map, we assign coordinates. We assign north, south, and the east and the west, and we would give a bearing in addition to a distance. So we're going to have to do sort of the same thing, but what physicists did and what Newton did is basically say, okay, this is a problem. We can't just put a single number on this motion from one place to another. We need a quantity that does a better job of describing these kinds of mathematical ideas. We want to be able to add what we took for day 1 to what we took for day 2 to what we took for day 3 to what we took to day 4, and figure out how to get from here to there directly without having to go sort of the long way around. And so we go to mathematicians and we say, numbers aren't just simple numbers aren't working well enough for us. We need a new thing that will do what we want it to, that will describe this motion in 2 or 3 dimensional space. And so what the mathematicians come back to us with is this concept of a vector. And so one of the things that seems to be confusing a lot of people out there is the difference between vectors and scalars. And so I want to go through that a little bit. And Newton 1 requires it. If we're going to specify the state of a system, we're going to have to use vectors to do so, because using simple numbers are not good enough. We simply can't do what we want to do with numbers. Even when using positive and negative numbers, we can't do it for 2 dimensions and 3 dimensions in space. So the mathematicians come back and they say, we have these quantities called vectors, but you have to be able to do a couple things to use them. You have to figure out that if you're going to call something a vector, you have to figure out how to add it, how to add 2 vectors together. And you're going to have to figure out how to multiply those vectors by numbers. So we think about this and we say, okay, let's go back to our picture here. If we're imagining trying to move from here to here to here and seeing what the overall motion is, the direct motion, how do we do that? Well, if I want to go from here to here, that's just, if I do this arrow first and then this arrow next, I get from here to here. And if I want to go from here to here, I do this arrow first and then this arrow next and then this arrow next. And that's the same thing as going straight from here to here. Notice in each case what I'm doing is I'm taking one arrow and aligning its tail with the head of the previous arrow. And then I'm imagining that the adding of those 2 arrows is just going straight from here to here. So we're going to call that our rule for addition. So when we say we add vectors, we don't mean the same way we add numbers. We mean we add vectors, pointers in this case, in a head-to-tail fashion. Now, there are other kinds of vectors that you can do mathematically where you have a completely different rule for adding them. This is a special case, and it's the one that we decide, and we choose the rule that if we want to know what is the vector A plus B give us, if we take this operation, well, it's very simple. We draw the vector A, and then we draw the vector B starting at the end of vector A. So I'm just going to redraw the vector B here. And then what we will find is that we get a new vector, C, because that is just the vector that goes from where we started to our end point here. And this is called vector C, which is the sum of vectors A and B. Now, there are some important things you need to know about the rules for adding vectors. And The first thing is that when you add vectors, you have to get another vector back. So this isn't, we've added these two vectors and we've got another vector back. It also can't matter what order we add vectors in. So if I start with B, so here's my vector B, and then I do A, didn't draw that very well. Let me get a little bit better angle here. And then I do A, I'm going to get the same vector here, the same arrow, starting here and going down, starting here and going down. I get the same arrow regardless of if I do A plus B or B plus A. They will both still give me the same vector C. So there are several rules that this addition has to follow. You have to be able to do them in any order you want to. Let's go back here, and what you'll see is that if you do these vectors in any order that we want, say that we do this one first, we go this way first from here, and then we do this one second, we go this way second from here, and then we do this one last, what we'll end up with is at the same spot anyway. So again, thinking about this moving on terrain, if you move 5 miles east, then 5 miles north, then 5 miles west, you end up 5 miles north of where you started. And it doesn't matter what order you do those in, you're going to end up at the same place as long as you do all three of them. So there are lots of rules for adding vectors, but this is the rule for how to add vectors, and it's called the addition of vector rule. All right, mathematician says, okay, good, you've got the first thing checked off. Now you have to figure out how you're going to multiply a vector by a number. Now, why would we want to do that? Because I might say something like, I moved 2 times further today than yesterday. Well, that has to have a meaning. We know that makes sense. If I tell you I moved twice as far in the same direction today as I did yesterday, then that's a possible motion. So it's really simple. All we do is we think, okay, how are we going to imagine multiplying a vector by a number? Well, let's take 2 vectors and add them together, but let's let those 2 vectors be the same vector. So this would be like I moved 2 miles this direction, and then I moved 2 miles again this direction. Now, what we can say is that we can just call this new vector that's moving all at once, we can call that just twice the first vector. So our rule is that if we take a vector and multiply it by a number, then all we're doing is asking us to do that vector that many times, or to add that vector to itself that many times. So we can imagine, what is the vector 3a? Well, the vector 3a is just going to be doing a 3 times. 1, 2, 3. Adding those together, that gives me this vector, which is the vector 3a. So we have a rule now for multiplying a vector by a number. Now note that this is a way of scaling the vector. We take the vector and we scale it up to make it bigger or smaller by this number. So when someone says something is a scalar, a quote scalar, this is all that it means. A scalar is a number that you can multiply a vector by to increase its length or to scale it up or down. And it's just a number. It's a number. It may possibly have units. We're going to see in physics, since we're dealing with vectors that are physical quantities, and physical quantities have units, the scalars associated with them may also have units, but there are things that are just numbers. So we have 2 kinds of mathematical objects that we're dealing with. We have vectors, which are just these arrows, and we have numbers. And the numbers we can add and subtract and multiply and do all the kinds of normal things that we do with numbers. But the vectors, we have to follow these rules with. We can add them now, head to tail method, and we can multiply them by numbers. Now, the physicists would say that's all you need to have a vector. But then we would go back to them and say, yeah, but we really don't have a concept of direction with these definitions. I know that I can move north, or I can move east, or I can move 25 degrees east of north. I know that there's some angles associated with how I'm moving around. Can you give me another rule? And so the mathematicians go and work on it for a little while, and they come back and they say, we've got one more rule for you, and that's a new rule. It doesn't apply to all vectors, but it does apply to the vectors you want, and that's how we multiply vectors by other vectors. So this is a different multiplication than this one. This is, we take a vector and multiply it by a number, a scalar. We scale up a vector. Here we take a vector and multiply it by another vector. What in the world does this quantity mean? This is called the dot product. And the dot product is very, very simple. You just take the length of one vector times the length of the second vector and multiply that by the cosine of the angle between them. So here I've got vector A, here I've got vector B. What I would do is measure how long vector A is, so how far I walked in this direction, and I would measure how long vector V is, and that would tell me how far I walked in this direction. And then the dot product would be how long vector A is times how long vector B is divided by the times the cosine of the angle in between them. The length of a vector, if I have a vector A and I want to know how long it is, the way that I write that is by putting little bars around it. That's called the magnitude or the length of the vector. That gets really cumbersome, so a lot of times when we're indicating how long a vector is, the length of a vector we'll just write as a number, the name of the vector, without putting the arrow over top of it. So when I have an arrow over top of something, I'm actually talking about the arrow. When I have no arrow over top of it, I'm talking about the length of the arrow. And this length is a scalar. You could imagine that we could start with some smaller vector and multiply it by a, and if you do that vector a times, then you get this vector that's this long. So this length is in fact a scalar, and again, it's just a number. All right, so what exactly is this whole idea of dot product? Well, I'm not going to motivate what the dot product is and where it comes from. It does have to do with lengths and angles. But maybe you'll see why it's useful if we ask what is the dot product of a vector with itself. If I take a vector and multiply by itself, what do I get? Well, let's look at the rule. The rule says you take the length of the first vector times the length of the second vector. Well, they're the same vector, so you just take the length and square it. The length of the first one times the length of the first one again, that's the vector squared. And then we take the cosine of the angle. Well, when a vector is sitting on top of itself, it doesn't have an angle between it and itself. Or another way of saying is that the theta, the angle here, is 0 degrees. And the cosine of theta, when theta is 0 degrees, is 1. I really should have here a cosine of 0 degrees is 1. And so cosine of 0 degrees is 1. That just goes away, so that's just 1. And so the dot product of a vector with itself is just its length squared. Or another way of saying that is if you take the dot product of a vector and the square root of that will give you the length of the vector. So in some sense, this multiplication by vectors is a way of generalizing lengths, and it explains lengths and angles. And we're going to see where this naturally comes up when talking about physics. We're going to see that this definition makes a whole lot of sense and comes directly from the ideas of forces and work. And we'll see that the dot product is an important quantity when it comes to talking about energy and forces and work. Okay.